Imagine that you're walking through a maze and you need to take a left turn and then you take a right turn and then another right. Well, you hit a wall. That's a dead end. Now what do? You go back at this point, retrace your steps to the last fork and try a different direction. So that's what you do, right? That instinct, try something and then undo it when it fails. This is the idea behind today's topic. And that's it. That's the whole lecture. And we could stop right here. But, it's called backtracking. And it turns out to be one of the most powerful algorithmic strategies in this course. So today we turn that instinct into precise code. By the end, you'll have a reasonable template that'll work on any backtracking problem. Welcome to lecture number 5, backtracking part 1, building and abandoning solutions. 3 goals today, basically. First, we apply backtracking template to several different problems, sequences, numbers, and a grid. And second, trace a backtracking function by hand so you can predict exactly what it's doing at each step. And third, internalize a reasonable 5-slot template. 5 slots, that is. So fill them in and the code writes itself. Every backtracking algorithm uses 3 moves, just 3, So move number 1, step forward, pick a candidate and go deeper into the search. In code, that's choose plus explore. Move number 2, hit a dead end and step back. Undo the last choice and try a different one. That's called unchoose. And move number 3, you reach the exit. That's a complete solution and that's the base case. So choose, explore, and unchoose. These 3 words appear in every single example today. So listen for them. We already know one recursion paradigm that's called divide and conquer. How is backtracking different as compared to that? So divide and conquer splits the problem into independent pieces and solve each piece, combines the result. So break apart, solve pieces and versions. So that's the essence of divide and conquer. But backtracking, that does something different. It builds a solution one choice at a time. Choose, explore deeper, and then unchoose on failure. It builds incrementally, step by step, and it undoes on failure. So same tool, that's recursion, but 2 very different strategies. Okay, so this is a really scary looking slide, but let me unpack this. What exactly are we building when we backtrack? That's the question. And the answer is a vector. A vector is a fancy way of saying a list of items. So essentially what we are doing and what we're building as a result of backtracking, that's just a list, an array of items. So an array filled 1 slot at a time. At each step, we pick from a set of candidates for the next slot. So look at the table on the screen, for example. For a path problem, the vector stores vertices. So each, what vertex it's on at each step. And for a permutation, candidates are going to be elements that are not used. For a subset, the candidates are simply, it's true or false. So in all of these cases, the algorithm stays the same. Only the candidates, the choice of candidates, that changes. Watch that vector being built slot by slot. So again, vector is just a fancy name for a list of items. We want all the binary strings of length 4 slots, each holding either a 0 or a 1. Choose 0 in slot number 1. We have 2 choices, 1 and 0, but let's suppose that we choose 0. And then we have 2 choices for slot 2. Let's say we pick 0 again for slot number 2 and slot number 3. So we are going now deeper and deeper. In slot number 4, we choose 0. And since the length of this list of items becomes 4, which was our intended length for the binary string, so this is one of the solutions that we have just found. But this is not the only solution. So how do we find other solutions? Now what we do is we unchoose 0 from slot 4 and we try the next candidate. So what candidates now we can try here? How many possibilities are there? So pause the video and think about it. Since we've already chosen 0, the only candidate that we can explore is 1. So we put 1 here, and we get another solution since the length of this list is essentially 4. So now what we do, since we have explored all of the possibilities for slot 4, we unchoose slot 4, and we also have to unchoose slot 3 because, again, we have explored all of the possibilities for slot 4. And now we choose a different value for slot 3. We have tried both candidates for slot 4, and we can, unchoose further. You can pop slot 4, you can pop slot 3, and back to slot 3 and choose a different value. Now we choose 1 for slot 3, and then for each value for slot 3, you have 2 choices for slot 4. Let's suppose that you choose 1 for slot 3 and 0 for slot 4. So that's one of the solutions. That's 0, 1, 0, 0. And if we think about it, this continues until all of the 16 possible strings they are found. The previous slide showed one of the examples, one of the problems that we can solve using the backtracking algorithm. Today in this lecture, we'll see 6 problems, and they'll be organized across 2 parallel ladders. So the first ladder is going to be the for loop shape, the binary strings and permutations, and then a maze. And the second ladder, that's going to be an include exclude shape. So that's going to have something called an all subsets. This is basically a problem in which we'll find all possible subsets of a set. And then we have a subset sum problem that we'll take a look at in detail. This is our first example. It has 0 constraints. And what do we mean by constraints? We will take a look at that very shortly. The problem is that we given in an integer, and we need to generate all possible 2 to the n binary strings of length n. So if n is 3, there are 2 to the 3, 8 possible binary strings, as you can see that listed on the screen here. And there are no constraints. We just pick either 0 or 1 for each slot, and there is nothing stopping us to do that. How do we find all of these systematically? We draw something called a decision tree, so that maps out every possible choice. So that's just a mental model. It's not code, essentially. So your code follows this under the hood, but this kind of a decision tree we can observe in pretty much a lot of backtracking algorithms and recursive algorithms and so on. So think of it this way. Each circle is a decision point. You have to decide what choice you need to make. And then each green box is one complete outcome. Every path from top to the green box, that's one sequence of choices. So for example, from the top, you choose D, and then at this point, you have choice. Either you can choose D or you can choose C, but you chose B, and your sequence becomes D and B at this green rectangle, which I've just highlighted. So decision tree is just a picture of what if I pick this, and then what happens. Here is a tree for n equals 3. The first level, we choose 0 or 1. And at the second level, if we choose 0, we still again have the choice to choose either 0 or a 1. And then at the third level, it's the same again. So each route to leaves, so these are the green boxes, they are leaves basically. So they define the entire sequence that we have just found. And this top node from where everything begins, that's called the root. So each root to leaf path spells one binary string. So that's 0. And then if you choose 0, and then if you choose 0, so that's 0, 0, 0, one possible binary string with 3 zeros. And then you can choose another path, 1, and then 0, and then 1. So that's another possible string at the end. And this leftmost branch is going to be, a rightmost branch, for example, is going to be 1, 1, and 1. That's the string that we have here. Another thing that I want to notice is the order. The algorithm finishes the leftmost branch completely, 0, 0, 0, as you can see here. And then it goes back to the fork here, and then it chooses the other option, which was 1, because we didn't choose that early. Once we pick the other option. So we have another string, which is 001. And then we go back from there. We have exhausted all possibilities at this node. We go back from here to this node. We have still one choice to explore, and we do that. So we keep on doing that. And this is something called, again, you don't have to know this in detail, but this way of moving down this kind of a decision tree from the top node, which is the root, to the bottom node. These green ones, these are called the leaves, is something called depth first search. Depth first search meaning that you go really deep first and you explore the each branch completely, and then you come back. So now let's take a look at some code. Here's the setup. One function that's called generate binary strings that take one argument. That's the number of digits that we want to create. This is going to be the length of the binary strings that we want to generate. So inside we have two lists. One is an empty list called results, and the other is an empty list called current. So result collects finished strings. Basically, this is going to be collecting all of the, the solutions. 000 is one solution, 001 is another solution, and 002 is another, 010 is another solution, and so on. And this is going to contain at the end all of the possible substrings of length. If this is 3, then it's going to contain all the length 3. And current is the partial solution that we are trying to build. And backtrack is an inner function, as we have seen this already in our recursion lectures. So this is a helper function, and this is the actual function where the actual recursion happens, basically, the real work. And line number 6, 7, and 8, this piece of code that you see, this if condition. So this is something called the base case. In the base case, what we are doing here is we are checking if our current, the partial solution, has got the required number of digits, since we are adding stuff into the current. So if that's the case, we have, reached at the end. So if you take a look at this tree again, we go from the top node bottom by choosing 0. Are we there yet? No, the current only contains 0. And then we go down by choosing 0. So now at this point, it has got only 2 digits, but we need 3. So now we choose either 0 or 1. Let's say we choose 1, and then we have 001. And now at this stage, this is the base case, since the length is the required length. And then we choose that. We add this to the results. And essentially, this is important that you add the copy of the current to the results, because current is going to be always changing. And then you simply return. So this return, basically, it really matters. It sends us back up to the tree and to try the next branch. The base case handles reaching a leaf. Now, the heart of the algorithm. These 3 lines, line number 2, 3, and 4, that you see here with the comments choose, explore, and unchoose. So these 3 lines define the backtracking. And what we're doing here is we are looping over choices. So how many possible choices we have? We have 2 choices, either 0 or 1, if you want to generate binary strings. So for each choice, these 3 things need to happen. Number 1, we need to choose the choice. We append it to the list of our current partial solution called choose. And then we backtrack recursively. And this is the explore phase. We explore, the subtree that goes deeper down. And then we pop the last character off. We unchoose that choice from the list of choices. And now the question is, let's say we delete this line number 4, current.pop. What happens then? So pause the video and think about it, and let's see if you can get it right. Okay, so this pop is what separates backtracking from plain recursion. Take it out, and the current grows forever. You're not popping anything from the current. You're not unchoosing. You're just choosing and adding choices to the partial solution. So it just grows without any boundaries. And the choices pile up. And what's the result? It's garbage. So accompanied with your lecture assets, you have many files, and one of the files is also these ones, the traced ones. When you run the algorithms, and you'll see this kind of a tree based structure. So where you choose something and then you explore it and then you choose stuff again. And then it tells you whether the base case is hit by the algorithm or not. And then once the base case is hit, then you unchoose by going back up to the parent and then you choose a different thing. And that's basically a tracing of the algorithm. So I encourage you to run these examples before proceeding, and pause the video and do it. And once you're done, then we can go to the next slide. All right, so this is the key insight hiding in that trace. The pop is not cleanup code. It's not an afterthought. It's half of the algorithm. Without it, every solution after the first one is completely wrong. So quick check for n equals 4. How many leaf nodes does this decision tree will have? How many internal nodes will it have? So pause the video, think about it for 5 seconds, and then we come back. All right, leaves are going to be leaves, to recall how many possible solutions that this tree is going to have. There's going to be 16 internal nodes. Internal nodes are the decision points where you decide whether you need to pick 1 or 0, for example. So those are going to be 15. So the total number of nodes in this binary tree is going to be 31. Binary strings had 0 constraints. We just picked these choices without any afterthought. Every path is valid. What happens when we add one rule? Each element can appear at most once. Binary strings, there are no constraints. Every path was valid. Now add one rule, and that is that each element can appear at most once. So one line of code, and that's all that changes. So it's pretty anticlimactic, but that's the whole point. The problem, let's say you're given a list of distinct integers, say 1, 2, and 3. You need to generate all n factorial permutations. So how many possible permutations are there for these 3 items? As we know from our high school math class that there are going to be 6 permutations. That's number of items factorial. 3 items, 6 permutations. But here's the striking number: 6 valid permutations out of all possible permutations, all possible sequences, actually. So all possible sequences, how many of there? Because if there are no constraints, then we can choose 1, and then we can choose 1 again. And then we can choose 1 again. So that's one possibility. But we are not allowed to do that, because once we have chosen an item, we cannot choose the same item again. So here, that restriction is in place. Now, I ask you a question. Where does this number 27 come from? Pause the video, think about it, and we continue in a bunch of seconds. 3 choices at each of the 3 positions. 3 times 3 times 3, we get 27. And the constraint eliminates 21 invalid candidates, because let's say 1, 1, 1 is not a valid candidate in this permutation. And that ratio actually gets more dramatic when n grows really large. So how does that constraint shape the decision tree? That's the question. At the root, we try 1 and 2 and 3. So there are 3 possible choices at the root, because we don't have any permutations at this point. It's just empty. Let's say we choose 1. Once we have chosen 1, either we can choose 2 or we can choose 3, but we cannot choose 1. That node, that decision is not valid. That's out of the question. We cannot do that again. Similarly, if we are at the decision point 2, you can choose 1, you can choose 3, but you cannot choose 2. So that's also out of the question here. So this red color X mark show where the condition prunes the branch. Prunes mean to selectively ignore or throw away a branch. about 60% of the search space is gone. And the saving is really huge and it's really big. All right, so look at this code here. I pause the video and I want you to find the single constraint that transforms the binary strings code into finding all possible permutations code. So pause the video, think about it, and we'll proceed in a couple of seconds. The skeleton is actually identical to binary strings. We have the result, we have the current, and again, a helper function called backtrack. So similarly, we again have pretty much the same base case. It's all the same as of this point. The for loop that looks pretty much like the same, but in this case, the previously we had only two choices, 0 and 1. Here we have multiple choices because that's the factorial of those many items. And for every single choice, we need to do these things that we saw already. So these look the same, exactly the same. Actually, we choose an item, then we backtrack recursively, and then we pop that item and choose some other thing. The thing that looks different is this thing over here, this condition. So what is this doing? Well, actually, the for loop is going to iterate over all items. But right here, this condition, that's the single line. And this is basically the constraint, the condition. And already in our, is this item already in our partial solution? If we have already selected this item in our partial solution, then we completely skip it and we continue straight up to the next iteration. And again, everything below this is identical to the previous binary strings algorithm. Exactly same 3 steps. So everything else, it's unchanged. The only thing that was new is this condition line number 9 and 10 that we added. And we are now choosing the items selectively in our current solution. Choose, explore, and unchoose, and you do that based on a condition. So basically, this entire template, the skeleton, remains very, very similar. The only things that changed were the choices. This this skip check is an example of a bigger idea that's called pruning. And what's the skip check? That's basically this continue part here. If the condition fails, you go straight back to the start of the this loop, and you do not call the recursion in this case. So if the condition fails, you go straight back. If condition passes, only then you do recursion. This skip actually is called pruning. Without pruning, without neglecting this decision, we explore every single branch, even the branches that we already know that give us the wrong solution, that lead us nowhere. So for example, 111 is not a valid permutation. So why bother exploring that branch when we already know that this is not going to lead anywhere? But with pruning, if a partial solution already violates a constraint, then you completely skip it, skip the entire subtree underneath it. So this is going to be a huge saving for us. And we never visit its children. So we cut the branch and we move on. So that's what we do. How much work does pruning save actually? Without the condition, we have 27 sequences, and many of these are invalid ones. But with condition, you only have 6 permutations, and every single one is valid. So for n equals 10, what happens then? Well, the difference is staggering. Without the condition, there are 10 billion sequences, and with the condition, there are about 3.6 million. So that's an extremely huge difference. So conditions are what make backtracking practical enough to do. All right, so core idea, core insight of this section. Why waste time exploring something that we already know is invalid? The conditions don't just filter invalid results, they cut entire subtrees, and that's where real savings come from. A quick check. Without the condition, how many permutations would we generate for n equals 4? So that's going to be 256. And with the condition, So basically, we are pruning all of the invalid results. So that's going to be a lot lesser than that, 24. So that's more than a 10 times reduction, basically. So these two examples of backtracking so far, we saw the binary strings and then we saw the permutation. They look, very similar, almost identical. And that's not a coincidence. That's a template underneath. Both these examples, follow the same skeleton. There are 5 slots. Every backtracking algorithm fills the same 5 slots. Number 1, that's the goal test. Is our partial solution complete? And then choices, what can we add to this step? And then you actually choose and add the choice to the partial solutions. And then you explore, you proceed recursively. You go down the path and then you explore the entire subtree. And then once you have explored everything, you come back and then you unchoose, basically. That's the unchoose step. So these 5 steps, they are crucial to every backtracking algorithm. And unchoose is going to remove the choice, is going to restore the state. Identify these 5 pieces for any problem and you can write the solutions. That's the cheat code, basically. You can solve pretty much any backtracking algorithm with this. So does it hold up? Check it against the 2 examples we have seen so far. So essentially what we have here is the for loop mapping table, binary strings on the left and permutations on the right. And look at the rows, for example. Choose, append in both cases. Unchoose, that's pop in both cases. Explore, that's also backtrack in both cases. So which row is the only one that is different? And that's the choice ones. The choices are different here. Binary strings loop over 0 and 1 with no filter, while permutations loop over all of the items, but it skips those that are already placed in the current choice. So it's exactly the same skeleton, but the different choices. That's a different shape we haven't seen yet. Here's an empty table, question mark in every cell. So keep in mind that after the next 2 examples, all subsets and subset sums, will come back and fill in every slot in this table. Now the second shape, essentially, instead of looping over choices, we make a yes/no decision about each element, whether we want to include it or we want to exclude it. Binary strings and permutations use a for loop. This next structure is fundamentally different. For each element, there is one question. Do we include it or do we exclude it? There is no for loop. This is just a binary yes/no decision at each step. So the problem is to generate all subsets of, let's say, 1, 2, and 3. Now, we know that from our math class that this is something called a power set, and all possible subsets of a set is 2 to the 3 in this case, and that's 8 total subsets, including the empty set. So how does the code differ, actually? Well, first thing that you note here is there is no for loop in this case. So instead, there are 2 explicit recursive calls, and that means there are 2 branches. So the first recursive call is this one in line number 10, and the second recursive call is this one in line number 13. Branch 1, that includes the current element, basically. We append it. This is the choose step. And then recurse with the next index, that is the explore item. And then we get back, we pop and we unchoose. So it's next step in line number 11 here. So branch 1 was include, but what about the branch 2? That is basically you exclude. Excluding means that you don't even append and explore and unchoose. You just explore without choosing the item. So you don't choose and then you do not unchoose. You just explore without it. So that's what exclude means. There are 2 branches. Now the question is the following. Why does only the include branch need a pop in line number 11? So pause the video, think about it. Okay, the base case. When the index, in this case here, from line numbers 5 to 7. So when the index reaches the end of the list, that's the base case. And whatever's in the current at that point is one complete subset. So essentially what we are doing here is the following. So let's say we have a set and we have 3 elements here, 1, 2, and 3. So we start at the beginning. So this is our index number 0. We pick this, we skip this, and we pick that. And while we're doing that, our index is moving forward. And what's the terminating condition? As soon as our index is at the end of the list, we know that we have picked some items and we have skipped some items. And so that's going to be our subset. Now, picture this decision tree. The top level include 1 or exclude 1. So that's the why a question mark is in there. So let's say if we include 1 in the set, then we have a choice to include 2 in it or not. So that's the same question, regardless of what decision we took about the 1. And at the bottom level, we include 3 or we exclude 3. So there are 8 total leaves, and the leftmost leaf, this leftmost sequence is 1, 2, and 3 in this order. So that includes basically everything. And the empty set is at the right-hand side, because at the topmost decision, we didn't choose 1, and then we could have chosen 2, but we didn't do that. And then we could have chosen 3, and we didn't also do that. So we didn't choose anything, and that results in an empty list, empty set. So same 8 outputs as a binary string of length 3. Is that a coincidence? Well, definitely not. So 2 structures side by side. The for loop structures that you see at the left side here, that loops over choices at each step. The branching factor varies. So there can be many choices at each single step. There can be 2 in our binary case, and then there can be a lot more than 2 in our permutation case. But the exclude step, the structure that we just saw for the subsets, so that's always a binary decision tree, because for each element, no matter what the element is, we are deciding whether we need to include it in the solution or we need to exclude it from the solution. So both use choose, explore, and unchoose. Both are backtracking, and the shape depends on, and the structure basically depends on how you frame the problem. All of the subsets generate every single subset, and there are no filters. So what if we want only the subsets that add up to a single value, a target value, add a running sum, for example, or some kind of a condition? So same jump we made from binary strings to permutations, but now in the include, exclude world. Parallel is deliberate. Binary strings, there are no constraints. Permutations, there is one constraint. We added one actually. And all subsets, there are no constraints, but that's a different structure. So now in subset sum, we use the same structure as the subsets one, but we add conditions in this case. So same pattern, same structure. 2 new ideas here: a running sum that tracks how much we have included so far, and a condition that stops early when the sum exceeds the target. So for example, given a list of numbers here, and that's the target that we're looking for, you need to find all subsets. And if you add values of those subsets, it needs to come up exactly 7. So how many subsets are there that sum up to 7? Your program needs to find that. So pause the video, think about it, and give it a shot, and we'll resume after a couple of seconds. All right. Now, in this case, we have 3 base cases, not just 1. So the first base case is the running sum. That is essentially, we are comparing whether it's equal to our target or not. So once that's become equal to our target, we know that we have achieved our goal, and we can add that subset to our set of results, and we can return from here. The second base case is essentially, obviously, we need to check whether are we the index reached the end of the list or not. So we have considered every element in this case, and we didn't hit the target. So that's our second base case, and we simply return from there. We return empty-handed actually. And whether the running sum is greater than target, so that's also a condition that is false, and there is no reason for continuing in this direction. So once the running sum is greater than our target, we know that no matter what items we add in that subset, it's not going to fulfill our condition. So you just return from here, cut your losses, and prune the entire subtree that we talked about earlier. So it's going to make your algorithm a little bit faster, actually a lot faster. Line number 10 is actually something called an early termination. It doesn't change what we find, but it avoids wasting time on branches that can't possibly work. But after we have seen the base cases, now the branches almost identical to our subset problem here. So again, we have two branches. One is including and the other one is excluding. Include, you append the element, you do a recursive call with the next index, and then running sum plus the element's value, and then you pop. And similarly, in the exclude case, we do not include that element. We simply increase our index, and we do not add the element in our running case, running sum, and we make the recursive call. So there is nothing here to choose and nothing here to unchoose in this second branch. So it's the same structure, only difference is the pruning condition on the previous slide. Back to the table from earlier, time to fill this in. All subsets, the goal is, the thing that we are trying to test here is whether the index is equal to the length of items list, basically. And choices are include or exclude. Whether we add the item in the current solution or not. And then we have choose. Choose is simply to append the element. And then we explore using a recursive call, and then unchoose using a pop operation. So what about the subset sum here? The goal is a tiny bit different. So it's to test the running sum equals the target. So choices are the same. We also do exclude and include and exclude in this case, but we have a condition. So that condition essentially prunes when the sum tries to exceed the value of the sum. So that's one extra condition that we are doing here in the subset sum. So backtracking is pretty much the same, and unchoose is pretty much the same. So two tables, one template, add a condition, skeleton stays pretty much identical. So same pattern as the for loop table structure that we saw previously. Same pattern as the for loop table, add a condition, the skeleton stays exactly the same. There are two tables and exactly one template. Both tables pretty much follow the same template, and the condition reduces work without changing the answer. So what's the worst case running time or worst case complexity? It's still big of 2 power n, this exponential. So back to the for loop structure, but now this time we are finding a path through a maze that the example that we saw in the first slide. Remember the maze from the opening? Try a direction, for example. Let's try to hit a dead end. Let's keep on pressing next. So we go forward, There is only one choice to go forward here. We do that. Now there's only one choice to move forward here. We do that. And still we have only one choice to move forward. But at this point, we have two choices. We could either go left or we could either go right. So let's randomly go to the right. Okay, fine. So we keep on going. We could have gone to the left and we could have then, pressed the exit. But now we didn't do that. We went in the opposite direction. So keep on going and until we hit a dead end. All right, now there's no place to go. Now what? Now we start backtracking. We get one step back. Are there any other routes to explore? No, there are not. So we keep on backtracking until we go back to our fork here at this point where we take the wrong turn here. Now at this point, there were two choices. One was left, one was right, but we already explored the left side. So the only possibility is now to go to the right side. And we do that. We press next, and that's that's that. So basically, that's the path from start to end. And that's what the green path shows. Basically, your algorithm not only needs to show that there is a path that exists from the start to the end, but it also needs to show, remember that what exactly that path is. And there could be many paths there in a maze, in a bigger maze, for example. And potentially your algorithm will be powerful enough to remember all of the possible paths from one point to another point. So this is the solution. Okay. So how do we solve this? There are 4 directions: up, down, left, and right. So each one is a row offset and a column offset. So the first one is the row. And as you go down, your row increases. As you go up, your row decreases. So up is -1. First component. This is not XY. This is row and column. Keep that in mind. So you have then down, you have left direction and right directions. Once we have made the directions, then we have a helper function which tells us whether a given row and column is it valid. So what do we mean by valid? Well, is the row in bounds? Is the column in bounds? Is the cell open, or is it a wall? Is it already visited, or or is it an untracked, unvisited cell? So this is the responsibility of is valid function, basically. So this is actually a kind of the same idea as permutations. If the item is in the current solution, you prevent repeats. Now, this is the heart of the backtracking algorithm. Again, we have the base case, and then we have this for loop structure, and then we have a condition just like before, and then we choose, then we explore, and then we unchoose. But there are a little differences also. So the base case, essentially, are we at the required goal? That's the exit point. If that's the case, we simply return true. And then we have the for loop here. So what does this for loop do? Well, the for loop, essentially what it's doing is there are 4 directions, and the for loop is choosing directions from these possibilities: up, down, left, and right. It computes the new, once you have the direction, what it does in line number 5, it computes the new row and column of your current position. And then it checks whether your new position is a valid position or not, using the same helper function that we saw earlier. So if it's not a valid choice, then we simply continue. We go straight back to the next iteration, and we do not, call the backtracking function here. We only go to the backtracking and explore other choices if and only if we know that our choice was valid. Now, if our choice was valid, we append that to our current solution. So this path basically, it's not given in the slide, but if you see the accompanying code, you'll see that this list here path, that's the current path that you're building. So you add the current solution to the path, and then also add it to the visited set, basically. So this is the choose step. So you recursively go into the new cell, you explore that completely. And if the recursive call returns true, you say that we have found the path, and you simply return true there. And that's an immediate success, basically. But what if it returns false? If it returns false, it means that was a dead end. So we undo it, we pop it, and then we remove that current cell from the visited, and then we go straight back to our next iteration and test the next direction, essentially. All right, now what if you tried all 4 directions and none worked? You simply return false, sure. So that's a dead end. Well, one new pattern that we can see here, previous examples collected all of the solutions into a results list, but maze solver returns a Boolean instead. So true for goal found and false for a dead end. So that's the key line. If backtrack your new row and new column, if that returns true, you simply don't recursively find other solutions, and then you return at that point. You don't keep on searching. But what if we do not, we delete this statement? Let me show you the code here. What if we simply, remove this condition here from line number 10 and line number 11? What happens then? So in that case, the solver will find all possible paths, not just one. So that's very interesting point. But underneath, the template is exactly the same. That's the for loop that iterates over the 4 directions instead of a list of items. And the visited set plays the role of whether an item is chosen in the current solution or not. So think of it about this way. Why does the maze solver need a separate visited set, but binary strings doesn't need that separate visited set? Well, the maze can have cycles meaning loops. It can, go around and around in circles. And without knowing whether we visited the set already or not, we are going to just stuck in an infinite loop forever and ever. So that's why we need a visited set, but we do not need that in the binary strings or any other example that we did earlier. So binary strings are always, they extend forward and they don't go into a loop, and each step adds a new digit, and there is no revisiting a previous state and no cycles. So that's why there's no visited set required in that case. All right. In this lecture, we have seen about 6 examples and 2 different structures. Now it's your turn. All right. So switching gears, open your code editor and open up the file. This is accompanied in your zip folder that is provided with this lecture. This is called example binary string traced. So before you run it, you need to predict this output, and then you run it with n equals 3 and see what happens. So does 000 appears before or after 001 in the output, and how many total strings are generated on the screen? So pause this video and write down your prediction, and then see you after a couple of seconds. All right. Now, what I want you guys to do is open up the file called generate binary strings in your editor. So this is not the traced one. This is the simple one. Now run it with n equals 3 and watch what happens in the output. So essentially, this is exactly the code that we were looking at in our lecture. And when we run it, it generates all strings of length 3. We choose, we explore, and then we unchoose. And we stop as soon as our current solution is equal to the number of digits in the binary string that we're looking for. And okay, now the second instruction, remove the current.pop call from your code. Okay, let's do that. Let's remove the unchoose code. Actually, we can comment it out and then we can run it again. We don't have to save it. So if we run it now, watch what happens, the output, basically. So output is essentially, it just keeps on going and it doesn't stop until it terminates your program and says that maximum recursion depth is exceeding while calling the Python object. So that's a mess, essentially. A string just keeps getting, longer and longer. We are appending in the current solution, but we are not popping it off. And only a couple of times it goes into the base case exactly when the size of the current list is equal to the number of digits. But other than that, if it's larger or smaller, it simply, exits out of, it doesn't go into the base case, and then it simply is stuck in the recursive cycle here. So this is exactly what happens when you forget to undo. And, so you have to be very careful. No pop means no backtracking, and algorithm cannot undo its choices. It moves forward forever and ever. All right, we broke it, but how about we extend this? So here's what I want you guys to do now. Pause the video, and here's your task. Generate all ternary strings, that is digits 0, 1, and 2. So instead of binary strings, now we have all possible ternary strings. So one possible ternary string could be So it's a base 3 number kind of. So it could be, let me actually clean this up. 0, 0, 0, then you have 1, 1, 1, and then this is also valid ternary number, and 3, 3, 3. No, you have just 0, 1, and 2. 0, 1, 2 is a valid number, and so on. So think about it, pause the video, and let's see if you can modify the binary string algorithm and generate these ternary strings from that. And let me give you a hint. It's just one line that changes. So even before you start writing code, how many strings does this algorithm need to produce for a string of size 3? All right, ready for the solution? Well, the only change that you need to do is you need to include an extra choice there. You change 0, 1 to 0, 1, and 2. And the result is going to be 3 to the 3. So 3 choices exactly for each slot. So that's 3 into 3 into 3, 27 total strings. So did you do it? Did you change more than one line? If you did, then you go back and you look at the template. So the skeleton is fixed. That's the whole point of, backtracking skeleton code. So we are almost at the end now. Now we have 4 things to take away. One, backtracking builds solutions incrementally. We choose, we explore, and we unchoose. And second thing is that the pop thing here. So this is not optional. This is actually half of the algorithm. Without it, everything breaks and nothing works. And the third thing that is important is that the conditions, they cut invalid branches, less work, same answer. That's called pruning. And the fourth thing is that the 5-slot template that you saw that maps basically goal test choices, we choose, explore, and unchoose. You identify all these 5 steps for any given algorithm, and that's pretty much it. That's the exact thing that you need to do. That's 95% of work that you need to do, is just to identify these 5 steps. And once you do that, your backtracking algorithm is already written. And here's the big picture. There are 2 variants, as you can say, or shapes of these backtracking algorithms that we saw in this lecture. The for loop variant, it iterates over choices. And the examples with binary strings, permutations, and the maze example that we saw. And the include, exclude variant, it makes a yes/no decision for every single element. And the examples were all subsets and subset sum problems that we saw. Even though they're a little bit different, these 2 variants from each other, but overall template is pretty much identical under the hood. Today we built the basics, and next time we push the constraints even further. The next lecture is going to be 3 problems that we will probably take a look at: the word search, and n queens, and the Sudoku puzzle. So word search is a bridge from the maze that we just did in this lecture. So we navigate a grid, but match characters in a target word, basically. So it's grid plus string matching. And the next problem, that's the n queens. So 3 interacting constraints: the rows, the columns, and the diagonals. The 3 conditions, they need to work together simultaneously. And this thing here, Sudoku, that's the capstone. In this case, in all of these 3 problems, the overall backtracking structure is pretty much exactly the same. So what changes is the choices and the constraints, the conditions that tells whether a certain choice that you choose is valid or not. And in these problems, the choices essentially are going to be progressively harder or complex as you go down. So that's it for today. And practice the exercises, run the trace versions, and make sure that you fill in the 5-slot template from memory. So see you in the next lecture. Bye-bye.